Okay, so yeah, we're back to MDPs and all that. Yeah, so were there any questions from the last time? We did like value iteration and policy iteration. So maybe let's just do a kind of recap because there are a couple of ideas here. So what we did was like MDPs, and we had states, we had actions, and we had transitions and rewards. So they were like so just MDPs, and I'm just doing a recap. Okay. Yeah, so states, actions, and transitions. So each of the transitions have some probabilities. So from a state, you take an action, and what we said is that the next state is not known with full certainty. There's some probability, and there is a reward that you get. And your goal is to maximize the long-term rewards, right? And we saw examples which can be cast as MDPs. So there was this racing car example which we came up with, and so there were a couple of problems that we studied. So what happened here was policies were of interest. So a policy was something, it was like a mapping from a state to an action, so states to actions. Okay, so this was like a function. And so this was, we represented this as pi. Okay, and there were a couple of problems here. So there are different kinds of different policies possible. So one problem is evaluating a fixed policy, evaluating a fixed policy pi. Okay, so what this means is that pi, you got the actions at each state, the action you had to take was given to you from pi. So now how do you evaluate the policy? And that's where we defined these values of these states, okay, under pi. Okay, and we had this recursion where the idea was that you start from a state S, there are a couple of actions you can take, and there is an intermediate state which kind of models the randomness in the system, and that state comes in, and then finally what you have is another state S dash. Okay, and this process goes on. So in some sense it was like a chance agent. So this was the environment which was bringing in some noise, and so there was you could consider that as a chance agent in the context of multi agents that we saw. And so this was just what we wrote was, you take each of the possible states you can get to from some action. So here the action was pi of s. So it was a fixed action. And then we had the one-time reward plus gamma times v pi of s dash. Because v pi, so the value associated with this state was v pi, and that was discounted by gamma, and we had this. Okay, so this was about evaluating a fixed policy, and we saw that there are a couple of ways to, do the actual computation. One is an iterative manner, so an iterative method, and there was also something where we also saw like solving a system of equations. Okay. Okay, so v pi's were, so this vector is actually what you want to solve for, and you have the transitions and rewards and even gamma, and then you just solve the system. So there were two methods here. Okay, and the next part of it was about finding the best policy. Okay, and so here what we saw were the Bellman equations. Okay, so we saw the Bellman equations, and I'm just writing it again because some of you might still be getting just used to this, so that's why I'm just writing it again. So V star of S is what we said was the value. Okay, and so that's the best possible value, I mean, from the best policy. So this is like the optimal policy, the best or optimal policy. And we said V star S is, from a state S, there are a couple of actions. So which is the best possible action to take? Okay, so immediately there is a max coming in. So it's a max over all possible actions. Now for each action you take, suppose you fix this action, you land up in this Q state, and then there are a couple of possible states S dash you can get to, right? So what you have is S dash, and each of them has a probability like this. And again, you have R of SA S dash, the one step reward, plus gamma V star of S dash. Okay. So what this means is that at every step you are going to act optimally. So then what is the value of each of these states? Okay, so in this part, so this was, how we captured the optimal value. Okay, and to get the optimal policy, it's you just do an argmax. So pi star, the optimal policy was done using, argmax of A. So this value is what we called as Q of SA. So Q star actually, because you're always behaving optimally. So what we said is you just take the best action here. Okay, whatever maximizes this at each state. And there was an issue about solving this because we didn't have the base cases, right? So here we saw two algorithms, value iteration, right, where it's like you stop at some time steps. You start off with v0, so at time step 0, all the values are 0. So you have 0 time steps left, then the value is 0. Now you try to find what is vk plus 1 in terms of vk, in terms of vk, and you keep doing this, and after some time it converges. So that was value iteration. So maybe I wanted to also show you one more demo, but maybe we'll just finish the recap. So this was value iteration, and we saw that it takes some time steps to converge, but actually sometimes the policy. So at each step you can also find a pi k plus 1 using the values of vk plus 1. Okay, so you can at every step you can find a policy like that, and we saw the policy typically can converge faster. So can we do something focused at only the policies? So that's where we came to policy iteration. Okay, and here the idea was that you start off with a policy, start with policy pi. So you started with a policy pi, and then you try to keep getting better. Then evaluate the policy pi. So that is something we saw the two methods above, right? So there were two methods. So we basically looked at this iterative approach. Okay, so but nothing prevents, you can also solve the system if you wish. But the idea is basically this: evaluate the policy pi and get a better policy. Get a better policy. Okay, so it's like an iterative step where you start off with pi 0, then evaluate the policy pi 0, then get a better policy pi 1, and like that it goes. So basically you start off with some pi k and evaluate the policy pi k, and then get a better policy pi k plus 1, and this goes on. Okay, it's a loop, and at some point you converge. Okay, so these were, I just wanted to, put this in perspective because a couple of things that we saw. So maybe it was confusing that what exactly we were doing, because all these things look similar, but there's some difference actually. So were there any questions from on these topics? Was this clear to you all? All good? Can you just type in the chat box? Yes. All right. Okay, great. So I showed you one implementation. I don't know if you guys got a chance to, implement this for a toy example. Like if you implemented it, things will just get very clear. Okay, each of these when you see it in action. I just want to also demonstrate, how the value iteration idea works in your project. Okay, so in your assignment. So I think here you're asked to only do value iteration. So let's just see the grid world example. Okay, so the grid world, as I told you, is like you start off in some state, and there were like two terminal states. Okay, so in this case, the top rightmost corner was like a good state. If you somehow trace your way through this grid, and you exit from the top rightmost corner, you get a reward of 1. Okay, so that's the best. And if you exit from the red grade, which is just below, it's bad for you. You get -1. Okay. So now the thing is, like, you have the transition probabilities, all that is given, all the rewards, everything is coded up there. So what you need to do is you need to find the best policy. Okay, so what they've shown is, like, this is one sample policy where, at the bottom leftmost, you will go up. And if you are in this state, what is it? This is 1, 2, right? The coordinate 1. So the bottom leftmost is 1, 1, and this is 1, 2, right? In terms of coordinates. So if you're here, you will go up. If you're in this place, you will go right. And so this is these arrows here that is giving you some policy. Okay, so let's just see, the value iteration algorithm in action once, like some iterations. So what's going to happen is, maybe let me just go to a place like this. Okay, so I'll just copy this command. So I just want to show you what happens in iteration 0. Okay, so I'm just doing one iteration of grid world, or let's just see what it is at the start. So at the start, you don't know the values of any of these states, and everything is going to give you like 0. Okay, so this is the initialization of grid world basically. And so these arrows, it's just, there's no meaning here at the moment, because if you look at the Q value, so what these are is the Q values for each of these actions. For example, in this state, the bottom leftmost, all directions, if you go left, it's going to carry a reward of 0. If you go up, it's going to carry a reward of 0, and so on. Okay, so every action in every state has a value of 0. And of course, here, these are terminals, so that's why it's been marked for you as 1. Okay, and so this is a simulation, so we don't have to see that. So let's just do one iteration. So now after one iteration, what's happened is the Q values have been updated. So what you're seeing here are essentially the Q values, right? So remember, Q values were this part, right? The sum of so this is actually the expected value. So this is actually the expected value of R S A S dash plus gamma V star. So gamma V star S dash. Okay, so it's an expectation over S dash. And what you're seeing is, if you had, instead of V star, you had V0. So that's what the value iteration is doing. Then what is the expectation? So that is what you are seeing here. Okay, because you are seeing exactly like a look ahead of 1. Okay, one time step into the future, you have the values. So then what is the best now? So that's why all these other values are coming up as zeros, okay, because you still haven't been able to see 2 time steps ahead. Okay, so that's the concept in value iteration, the idea of truncating time steps. So now let us just see what happens after one more time step. Okay, so I'll just keep this here. Maybe I'll just run it in a... So we'll just do 2 iterations now. So at the end of the second iteration, what has happened? Right. So this is the values, of course. Now, oops, I'm very sorry again. Okay, let's just take this one. Yeah. So here it propagated to one more step before. Okay, so this is after 2 iterations. So what I'm seeing is I got one more set of Q values. Okay. And that's how it processes typically. It progresses in this way. You initially start off knowing nothing, and then you see what happens, when you could look ahead by 1 time step, and what happens if you could look ahead by 2 time steps. That's how it progresses. And so let's just see, after a couple of iterations. So maybe let's keep around 15 iterations. So here, this means that all the states have been visited at least once. Okay, you have had a chance to look at every state, what happens. And so this is the optimal policy. This is the policy after this many iterations. Okay, so it says that you should, if you're starting in the left, bottom left, you go up and you go right. So that's the best thing to do. And from here, from this, which is just below. So this is 1, 2, 3. So 3, 1. The coordinate 3, 1. The idea is you just go up and try to exit. Okay. In the process, it might happen that you land up here, but the value of that is quite small at the moment, what your estimate is. And the Q values are like this. Okay. So if you see at this state, right, are you able to see my cursor?
Yes, ma'am.
Yes, ma'am.
Yeah. So, right. So at this point, actually the value is 0.48. So it is actually the north action. If you go north, the value is 0.48, and that is the best action to take. And that is actually the value. Okay. So all these four are the Q values corresponding to each of the actions at this state. And yeah, the best becomes the value of that state. Okay. Yeah, this is just to demonstrate this to you. So any questions on this demo?
Ma'am, what if we give a very large number?
Large number of iterations?
Yes, ma'am.
Yeah, sure. So it will converge after some point of time. So let's take something like 50. Okay. So yeah, I mean, this process will go on. At some point, it will converge. Okay. So yeah, usually you give a large number of iterations so that you're sure that it will converge. And so I think this one, it converged actually pretty soon. So this was the optimal policy here.
Ma'am, for this position in the maze like 0.43, first row, second column, white showing arrow to the left.
Yeah. So let us see the
Because
Q. Yeah, the Q
because
values
ma'am,
here. Yes. So these are the Q values, right? Whatever it shows you is whatever the best Q value it was that it got. So this inferred that, if you go right at this point, right? If you go right, you're going to get a value of 0.42. Okay. The issue is that, you might end up, jumping into this pit, this -1. So it's like a trade-off, whether you will jump into the pit sooner or you will, go to the one which gave you a better reward sooner. And overall, like, what was the reward? So keeping all these factors in mind, this was the best. So 0.43, this was the best thing to do. Slightly
isn't it
better.
like something like a shortest path to get the highest reward?
Shortest path, yes, but because now there are these probabilities, right? At each
Yes.
state, there is a probability. Like if you take this action, like if you take the right action, there is a possibility that you won't go into this state. Rather, you might go into the other state, right? So if it was, yes, if it was just, a very deterministic thing that that where you're going to be, yes, it's like a shortest path. It's a shortest path with some rewards. The final reward to get to 1 versus -1. Okay, so you could consider the shortest path to get there and a reward, a trade-off between these two. But now because there are these, if you press the right arrow, you're not sure if you will go right or left. So because of that, there is some difference here.
Okay, ma'am. Got it.
Okay. Yeah. Okay. So yeah. So any more questions? So all these questions are really important. Okay, you should ask so that things get clear. Like there are the subtle points here which can end up getting missed. So you please ask. Okay, even anything that you have.
Excuse me, ma'am.
Yes.
Um, in this example, the agent does not know like with what probability it will go from one state to other, right? After choosing the action. So
Here,
is there any way
everything
to
is known. The probabilities are all known,
Okay, okay.
and that's how you are able to compute these values. Right? You don't know exactly which state you will be, but you know it in a probabilistic sense.
Yes, yes, okay.
Right? Was that the question, Advait?
Yes, yes, I got it.
Yeah. So we will do, actually, in fact, the next topic is what do you do if you don't know these probabilities? So we are going to head into that part. Okay. Anything else? Any new questions? Any other confusions regarding this topic? Okay. Okay, so that was just a quick recap. So now I just wanted to also tell you one more point about policy iteration, like about the complexity aspect. So we saw that in value iteration, each, because you're trying to find the very best at each time, because there's a max and a summation over the states. Okay, so here the complexity of each of these iterations was order of S square A, right? Because for each state, you're trying to iterate over all actions, and then you're trying to iterate over all the destination states. So there's an S square A factor coming in. Now in policy iteration, what's going to happen is the update is essentially this one. Okay, so it overcomes that iteration over the actions. Okay, so here what's going to be the complexity of each of the iterations? So this is an inner iteration, right? So this is where you're trying to evaluate a fixed policy using an iterative method. So what about this step? What is the complexity in terms of the state's actions? Can somebody answer? Attempt at it.
S into A.
S into A. So S, okay, let's take this. So S is because you have to do this for every state, right? And what about A? Why do you need A?
Sorry. Oh, S square. S, not A.
S square, right? Yeah, so this is complexity is order of S square, okay, for each iteration. So S1S for, for the value of each of the states you need to find. And internally, there is a summation over each of these S dash. So that is as many as the number of states. So that's where you have an order of S square complexity for each iteration. Okay, but there's a subtle difference here. The iteration is, there is again this thing, evaluating a policy that could get done multiple times. So this is, within evaluation of a single policy, each iteration takes order of S square. Okay, we are not, but overall, what has been observed is this is much faster than value iteration. Okay, so it's not a theoretical result that overall what is the complexity. It's just of each component iteration, this is the speed. Okay. And so now what I want to do is I just want to talk of a slightly different example. So maybe let me just start a new. Okay. Okay, open multiple things. Yeah. Yeah, so I'm just going to talk of another framework here, okay, slightly different class of problems, so which can also be, maybe cast as an MDP. So consider this case, right? Like there are two restaurants that you can go to. So if you're in the hostel now, and maybe, there is a nearby Domino's. Okay, so Domino's Pizza, that is one restaurant. And there is a new restaurant that has come up. So you've been to Domino's a couple of times. So have you all been to Domino's? Do you like Domino's? Because nobody is unfamiliar with Domino's, right? Yes, no? Instructions, trying to replicate some results. Okay. So for this, the deadline is October 6th. That's what I said. So okay, somebody else is watching my older YouTube lecture, it looks like. Yeah, I encourage you all to start. Okay, Karthik. Okay, fine. Anyways, yeah, so let's come back here. So the Domino's is one possible restaurant, and then there is a new restaurant in town. So Domino's Pizza, you've always been there and you love it. The new restaurant, you don't know. Okay, so some people have told you that it's very good. Some people have told you that it's not at all good. Okay, so so there are like these two possible rewards. Okay, so in the new restaurant, it could be either a 0 or maybe 100, or let's say even 200. Okay, and Domino's is always a constant. They're very consistent. They always give you a satisfaction of 100. Okay, so there's like a score that you give them. Okay, so yeah, so this is the setting. So now you want to decide like how to go. I mean, where should you go for food? Okay, because the thing is, like the new restaurant, there is some randomness here, because sometimes some people told you they're very good and some people told you that they're very bad. Okay, so this this problem of where to go to, that also you can write this as in the MDP framework, though we will see in a bit that you don't really need all the sophistication of an MDP. But let's consider the case where the states are maybe something like this: you're happy or you're sad. Okay, so if you go to the new restaurant and if you get a reward of 0, you're sad. Okay, so that's just the notion. It's very loose example. Okay, so let's just try to write this, right, like an MDP, like how we did. So there are two states here, happy and sad. And what are the actions possible here? You get the setting, right? What the two things are?
Yes, ma'am.
Yes. So what are the actions now?
So if you are happy and if you take Domino's pizza, then you will again land up in happy state.
Yes, exactly. So yeah, so the actions are either Domino's or the new restaurant, right? The two actions possible. Okay. So this is, I think that was Sahil, right?
Yes, ma'am.
Yeah, okay. So if you go to Domino's, then yeah, it's a consistent state. So you'll always, this is a probability of 1, and you're going to get a reward of 100. Okay. So this is this one. Now what happens if you go to the new restaurant?
So it will be based on the probability, like you get 0 or 100.
Okay. So let's say this probability, maybe they had like a point. Okay, let's be kind to them. It's 0.4 and 0.6. Okay. So yeah, at the happy state, if you went to the new restaurant with a probability 0.6, you will come back to the happy state, and there was a reward of 200. Now, if you, with probability 0.4, you would come to the sad state, and there was a reward of 0. Okay. Now, what about in the sad state? What happens here? If you went to Domino's, what would happen?
You would go to happy.
Back.
Return to happy state.
You would go to happy state, right? So this is again a probability of 1 and a reward of 100. And if you took the new restaurant, what would happen?
With 0.4 probability, we would remain in sad state, and with 0.6, we would go to happy.
Okay, so 0.4 probability you remain here, and the reward is 0. And with 0.6, you would go here, and the reward will be 200. Okay, so this is yeah, we've cast this problem as an MDP, and so actually in this kind of an example, is the states telling you anything? So there are two states here, happy and sad, right? Just observe it closely. Of course, we wrote it as two states because there were these two possible rewards that the new restaurant would give you, right? But really, are the states adding anything, right? Because there's a lot of symmetry here, right? Because the same set of actions, the same set of rewards, the same probabilities are going to happen in each of these states. So instead, so this was one way we modeled this problem. Now, alternatively, if you write it using just a single state, so let me just write it as a state B. Okay, and if I just compress all of these H and S states. I'm just compressing it into one. Okay, so what this would mean is I'm at whatever state I'm in. If I go to Domino's with high probability, with probability 1, I'm going to get a reward of 100. And whereas if I go to the new restaurant with probability 0.6, of course, now the probability is more for the rewards because I'm going to come back to the same state, but the reward is going to be 200. And, if I go to the new restaurant with probability 0.4, now the reward is going to be 0. And always I come back to the state. Okay, so, this is a homework for you. So try to find the optimal policy for both. There are two representations now. Try to find the optimal policy in terms of both and see what happens. Do they match? Do they not match? So ideally you should get that it matches, okay? Because for this example, the states are not really meaningful. Okay, so this kind of leads to another, class of problems. So what I also want to tell you is, here I gave you these numbers like this 0.4 and 0.6. Okay, but now suppose I don't tell you these values. So suppose these are unknown, these are not known. Okay, so what would you do? Right, so it's the same framework. These numbers are all there. This is 100, and the new restaurant is going to give you either 0 or 200. But you don't know how often they are good or what's the probability with which they are bad. Okay, now these probabilities, if you don't know, what would you do? Right, so this is something that all of you must have faced, right? Like there are different choices that you have, but you don't know clearly which is better, and there is some variability, right? So what would you do?
Might be we can check out the new restaurant around 10-15 times and see whether the reward is 200 or 0. And based on that, we can...
Yeah, based on that, then you decide which, you finally make an impression of what is good or what is not. Right? So, yeah, so maybe, let me just write it afresh. I'll just copy this part. So now this is all the information that you have. Don't know the probabilities. Okay. Okay. So what Sahil said is like you try the new restaurant few times. So maybe suppose you initially got like all zeros. So 3 times you went, you got zeros. What would you do? So next time, what do you do? Should you go to the Domino's pizza or should you give them some more chance?
Maybe we should give some more time.
Some more chance, right? Yeah, because maybe you were just unlucky at this point of time. Maybe they were just setting up and things were bad. So maybe you went few more times and maybe now next time you got 200. Okay, so basically this is the thing, like you will do some kind of an exploration and then you will see what is good. And based on that, you make a choice. So in the process, what you're going to do is like an experiment that you do. And so it's not that every time you'll be optimal. For example, if you look at each of these time steps, so these 3 times, if you had gone to Domino's Pizza, you'd have got 100, right? So overall, this was not the best thing to do, right? If you look at the overall reward, so this would have, instead, you would have got 100, 100, 100 if you went to Domino's. So the other possibility was 100, 100, 100, 200. So 200 is what here the new restaurant was better. So of course, this was the best thing to do. Okay, so this is happening because you don't know exactly the probabilities. Okay, and you're trying to ascertain your belief on what the probabilities are, and that's why there is some loss that you incur from the truly optimal. So optimal would have been something like this. Okay, so so in general, these kind of problems where there is something of the system that you don't know, and in very particular this kind of thing where you have these choices, and at each point you have to make a choice without knowing the probability of the rewards. This class of problems is called bandit problems. Okay. So there's an additional level of complexity. Somehow you have to learn the probability of, the performance of each of these options. And so that's the next level of sophistication that we are going to do. So in bandit problems, it's like, you don't have this notion of states. Okay, so it's like a single state captures everything. The main thing is about actions. Each of these actions have some probabilistic rewards. And then because of that, you have to decide what's the best thing to do. Okay, you could also, instead of Domino's, this could also be, another new restaurant. So there could be some probabilities here. So another variant is new restaurant 1, and there's two new restaurants. Okay, so here maybe it is like new restaurant 2 is 0, 200. So these are the possibilities. New restaurant 1 maybe something like 100 and maybe 300. Okay, so here this could also be a variant that arises. Okay, so of course you can model this with MDPs, but you don't know the probabilities, the underlying probabilities. So this is what is going to lead us to our next class of problems, reinforcement learning. Okay, so actually we are heading into learning kind of problems where you don't know the model. So very broadly speaking, so let me just write the framework. So reinforcement learning, what you do is there's an agent, okay, and there is an environment. Okay, so this is like how it was in MDPs itself. So the agent takes some action and the environment replies back with some reward. Okay. Now the agent again takes an action but doesn't know where the next state or what the probabilities are. Okay, and the environment again gives back a reward, and this process goes on, and the agent is trying to maximize the rewards that he can get. Okay, so the framework that reinforcement learning typically does is with an MDP itself. So the underlying model is an MDP. So there are states, there are actions, okay, then there are these transition probabilities, the transition function, and so this is a probability, and there's a reward, right? There's a reward function. Okay, but now the new catch is these two are unknown. These are not known to you beforehand. Okay, so all you know is there are these states, there are these actions. This is there. You have to do something. And beforehand, you will not know what's the probability of moving to another state. You will not know what is the reward that you're going to get. So it's actually there's no information, right? You are kind of in the puddle and you have to just decide what to do. Okay, so this is a framework, and what I told you here with bandits was one level of simplification where you didn't have the notion of states. You had this transition and rewards, but the states was implicitly there's just one state, and so you had to decide between an action, and so it was like actions and rewards, right? Only these two were there. So more general framework of RL has all these components, and that's what we're going to do now. Okay, so let's come back to the MDP framework. So let me just take the grid world example itself. Okay, so maybe this is an example from the Berkeley, RL example, or I think this was from the MDP example itself. So so these are, it's a very tiny toy grid world where there are these two terminal states. Okay, so there is an A and a D. So those are like terminal states. And, you have to somehow decide where to go. And now you don't have any information. Okay, there's nothing known to you. It's just that you can go left, right, up, down. These are the only possible actions. So in B, if you decide to go up, either you will go, you will always go right. Okay, there's no other possibility. But anyway, none of these things are known to you beforehand. Okay, so what will you do here? What's the idea? What is a possible thing to try here?
Could you
Guys?
tell the question again? I did not understand it.
No. So I'm just asking. So this is again, there's a toy grid world example, and there are these two states here, A, D. So those are like the terminal states. Okay, and you don't know any what the reward is going to be. So ignore this part. Okay, the second part. Forget about this. Just look at this grid. So you have to do something, right? You don't know anything about the rewards. You don't know about where you will land up if you take an action. So what are you going to do?
Ma'am, do
We
we know the
randomly
terminal
start choosing
states?
actions and see what reward we get till we reach the terminal state.
Yeah, exactly. Right. You just try something. So Tanuja, you were saying something.
Do
It
we
was
know that
Tanuja.
such a state is a terminal state when we enter it? Like if I'm
Yeah.
at C and if I take right,
Go ahead.
if I'm at C and if I head to right, I'll be in D, which is the terminal state. Then will I get to know that it is a terminal state or not?
You will get to know once you exit. So
Okay.
after D, once you are at D, only then you will know that this is a terminal state. Because the only option at D would be to exit, and only then you will know.
Yes, ma'am.
Right?
Then we'll probably try all the examples.
Yeah, you will try some couple of things, right? At B, you will take a right, you will come to C, then maybe you will go right, maybe you will go top. Some things you will try. Okay, so okay, yeah, so that's basically, even like in the other example of the restaurants, that's what you did, try out a few things. Okay, so let's talk of couple of issues here. Okay, so suppose you tried some things out. Okay, so that's the thing I've given here. There are these, so episode is like each trial. So the first time I tried, I did this. I took an east action at B, I went to C, and so there is some reward at each stage. So immediately I got a reward of -1 because I was staying in the grid for one more unit of time. And from C, what I did was I took an action east. I landed up in D. I got -1 again. And from D, I had to exit. There was no other possibility. And I got a reward of +10. Okay. So I did this once. Now, with this, could I say something? If I just did, so this is called an episode. So each time I try to, go over the possible sequence of actions, that is called one episode. So from where I start till I reach a terminal, that's called an episode. Okay, so episode 1 was this. And yeah, like if you, so this is an example where you got lucky, maybe you got a reward of 10 finally, and you don't know, you still don't know about the other states. Okay, so maybe you do some more episodes, you try to travel this grid once more. So the next time again the same thing happened. Okay, now maybe in the next instant, the third episode is maybe you start off with E. Okay, you don't start in B, rather you start in E, and then you see what possibilities happen. Okay, so now I've done this few times, and fourth time also something like this happened. Okay, now the fourth time what happened is I exited from A. Okay, and here I got a reward of -10. Okay, so now after this, so I've done it few times now. What can I say? Is there something I can say about the model, or what state is good and all that?
We could
Yes,
say
ma'am.
that A is a bad terminal state and D is a good terminal state.
D is a good terminal state, right? And yeah, so that is what we see from here. So somebody else also was saying something. So but Tanuja's, yeah, what Tanuja said is right. Did somebody else have some other thoughts?
We can say that from state C, it is more profitable to take east because it gave us plus 10 3 times and minus 10 just once.
Exactly. So in C, there were these, so there's something you have to also make use of the other states, right? So one thing what Tanuja said was between D and A, we know that D was a vector state. And at C, we know that, in C, there were these actions. So C, you go east, 3 times you hit a D and a -1. And one time, even though you took an east, you went to A, right? So this is where, the transition probabilities were coming into picture, and you got a reward of -1. Okay, so there's something you can say here as well. So about all these intermediate states as well. Okay, so in some sense, what you can do is you can get an estimate for the transition probabilities, and you can also estimate the rewards. So in this example, of course, the rewards are always, like +10 or -10. So this is fixed, but in more generally, even the rewards themselves could be random. Okay, the transition probabilities, you can have a probability of going to each of these states. And for each of these rewards, those themselves can also be random. Okay, so what you can do is, let me just bring this here. So you can get an estimate. You can actually try to learn the MDP now with this. Okay, so what is it that you know? You know the states, A, B, C, D, E are the states, the actions you know. So what you can learn from here is, if I was in B and I took an east option, and what's the probability that I'll land up in C? Okay, so based on what I see from these episodes, so this probability is going to be, what's this probability from here? If I see the fraction of times that I reached C from B when I took east.
1.
Exactly 1, right? Because that was these two events were responsible for that. Okay, now, so everything else was a 0 probability. Now, what about from C, if I took an east and reached D? What was this probability?
3/4.
3/4, right? So it's basically this one, and these were the 3, and there's one more here. So what's the other possibility? C going east and A, right? So this probability was 1/4, right? And so probability of C going east and hitting E. So based on these episodes, this probability was 0. Okay, and B also is 0. So yeah, so in this manner, you can try to fill out all the transition probabilities, and similarly for the rewards also. So the reward, when you started from B and you took an east and landed up in C. So what was this one?
-1.
-1, right? The same logic. So you just, sum over whatever outcomes you got, the rewards from these outcomes, and then you do a normalization. So like this, you can try to learn the transitions, you can learn the reward functions, and finally you can build an MDP, right? So now you have the entire MDP constructed. Use these. So this hat I've marked here because it's an estimate. This is not the exact probability, but what you are learning from your data. Okay, and so this is actually what is called a model-based RL. Okay, so let me just get the terminology right. Yeah, model-based learning. Okay, so where you're explicitly trying to learn a model, and then you can use your value iteration or policy iteration algorithms. Okay, but the thing is, there's some problem here. So can somebody identify what the problem can be?
Ma'am, I have a doubt.
Yes.
When we are at C and we move to east, why did we end up in A?
Yeah, so there is some underlying probabilistic thing here, right? Yeah, if you wanted, like, okay, ideally, if you want to go east, you think that you will land up in D, but maybe there's some issue with the grid board. Okay, so that's why there is some probabilistic thing happening. So it's exactly the same thing, right? Like you take this action, but finally there's something that the environment does, and it's not clear that you'll always land up in D. With some probability you will go to some other states. So it could be that maybe your keys are a problem, your keyboard, there's some malfunctioning there. Okay, or in general, like if like the example I gave earlier about if there's a robot which is actually trying to traverse the grid, there may be some controls for the robot which because of which like the robot decides to go right, but then some of the parts there is some malfunctioning there, and so maybe it has to go, it ends up going somewhere else. So there is a probability that that happens. It could be a small probability, or if it is a really old withered out robot, maybe there's a larger probability of that happening. Okay, so that's the reason why you know you take an east, but there is a chance that you will go to A. Okay, you're trying to capture what are all the possibilities that can happen, what can go wrong, what can go right, and things like that.
Yes, ma'am.
So it's basically the same assumptions that we started off with MDPs, right? Always there's a probability of going to some other state. For example, even maybe the racing car example that we had, right? So I guess that was here, right? So in the racing car example also, there was this chance, right? Like, the actions were fast and slow. So if you go fast, there's some probability you will be warm, but there's also a probability that the engine stays cool. Okay, so the similar idea even in grid world. So this grid is actually, it's just giving you a platform in which you can try out all these, it's like you can simulate all these steps. So yeah, so I think we're running out of time. So yeah, so model-based learning was this. So there are some flaws here. So maybe just think about what could go wrong with model-based learning, or is there something better you can do?
Actions are not defined.
So actions are defined. So what you know
No,
beforehand
ma'am.
is
Like if we are on C and if we press west, so what will happen? It is not defined in the.
no. So if you go west, you can either go to B, A, E, or D. Any of these can happen. That much you know,
Okay, ma'am.
right? It's okay. What was that your question, or you were trying to point out something else?
Trying to point out the mistake.
The mistake with this. Okay. Now I get it. So what you're saying is you did this few times, but you never saw what happened when you went west. That's what you're saying, right? So from C, you didn't get anything for west, and so you said that that action, nothing happened. So you're not learning anything about that. Yeah. So that is true. So you need to do this like many times. You need to have a lot of episodes before you can learn something meaningful, right? So that is one thing. And also in the process, you're like separating out the two things. You're doing a lot of learning, and and then you're again doing some effort in doing value iteration and policy iteration. Okay, so there's a lot of waste that's happening in some sense. So can we do something better? Okay, so that's going to be the next topic. Okay, so maybe I'll stop here, and I'll hang back for any questions. If not, we meet tomorrow. Okay, yeah, thanks.